All right, welcome in online members to your favorite class. Yes. All right, good audience today. We got at least 2. No, I'm just kidding. We have 6, but it was at least 2. I wasn't lying. Okay. Announcements. Your homework number 2 was due right now to my mailbox. Hopefully you got it in. I'll post homework number 3 on short fiber and particulate composites. I don't know, probably in the next day. All right. So look out for that. All right. Any questions? I don't think so. Not a lot of questions right now. So if no questions, let's go ahead and pick up where we left off then. And I will get the writing pad. And we will do the thing with the notes and the stuff. Hopefully we can finish up short fiber and particulate stuff today. We don't have a bunch. We don't have much left. We're a little behind on the schedule, but it's okay. Okay. Here we are. Back to reality. Oops, there goes gravity. All right, so when we left off, we were talking about short fiber composites. Specifically, we were talking about aligned short fiber composites. We had 2 models. One was a simplified model. And we used the simplified model to calculate E1 and E2. And the second was the Cox model, or what's called the shear lag model. And we were looking at the Cox model for calculating E1. The simplified model is exactly that, simplified. It uses modifications to help in psi to get you where you want to go. The Cox model is derived in an entirely different fashion. We went over that last time. So the simplified model was something like, all right, E1 comma 2, since they're both kind of ending up working the same way. Modulus of the matrix, 1 plus psi eta df all over 1 minus eta df, where eta is equal to property of the fiber. We can be specific here because we're looking at modulus. Modulus of the fiber over modulus of the matrix minus 1 divided by modulus of the fiber divided by modulus of the matrix plus xi. The difference here in calculating E1 and E2 is going to be that for E1, you're going to use xi equals 2L on D, where L is the length of the fiber, D is the diameter of the fiber. And for E2, you'll use xi equal to 2. This is the full simplified model. Okay. The shear lag model, the Cox model, that was kind of derived entirely differently. In the Cox model, we sort of assumed that there's a distribution that the fibers could actually hold when it comes to like their normal stress, saying that, we can't hold normal stress on the end of the fiber, but we can hold normal stress throughout the center of the fiber. So we took that and we ran with it using sort of the mechanics of material parallel model, assuming a mean stress that the fiber could hold. So here, the Cox model. The final form of this for modulus in the one direction looks something like this. Looks very similar to the rule of mixtures, except we have kind of a fudge factor. All right. So this is volume fraction fibers modulus in the one direction of the fibers times this new term, eta sub L, which is the shear lag factor, plus volume fraction of the matrix, property of the matrix, specifically here, modulus of the matrix. This is your Cox model. And here we have this sort of interesting new parameter. This is a shear lag parameter. We said here that eta L is equal to 1 minus the hyperbolic tangent, obviously, of BL on 2, divided by BL on 2, where this B term is also a little bit complicated. Modulus in one direction, the fibers, multiplied by the radius of the fiber squared, times the natural log, radius of the matrix over radius of the fiber. Remember, these are terms that we defined with that little model that we had. Those terms are generally related to the volume fraction. And the numerator here, 2GM. So this is your full Cox model. We got a question here in the chat. Yes, question.
I don't know if it's just me, but I can't see the screen.
Does anyone else have this problem?
I can see the screen just fine.
Okay.
Right,
Sophia, you might want to just leave and rejoin the meeting. That might help.
Yep, thanks. Sorry.
Okay, no problem. 2G sub M, where GM, this is the shear modulus of the matrix. So I defined all these terms last time. All right. So in your upcoming homework, yes, Justin? Is what? Oh, this will be in radians. Yes. Thank you for that. This hyperbolic tangent. It's so rad. I hope at least one of you laughed at that. Okay. All right. So that's about where we left off. And that kind of concludes the aligned short fiber portion. And we were getting into now the next sort of short fiber model, which was the partially aligned short fiber composites. It's funny because they're banging that pillar into the ground right now, and I can hear it from where I'm sitting right now. Yeah, exciting. So, you know, if you live next to that, that sucks. Just probably a lot of you. I mean, I only live like 3 blocks away from there. I don't really hear it that much, but I can imagine if you live right next door, that would be horrible. Okay, so partially aligned short fiber composites. Everyone's in here laughing. So they all know that it's true. All right. So for the partially aligned short fiber composites, we're more or less going to use the same model as the aligned short fiber composites, except with another fudge factor. Okay, similar to. But with an alignment parameter. So this will be similar to Cox model. And here's the general form. So for a partially aligned, again, just to draw the picture, so we all kind of remember sort of what a partially aligned composite looks like. All right, so this might be a composite that has partially aligned components. All right, so they're not all sort of in a similar direction or array, but they're kind of like sort of generally pointing in one direction, kind of, sort of, if you bend your head just right. Okay. So let's say we want to calculate modulus in a one direction, where we sort of arbitrarily just align a one direction. Okay? We'll just say, you know, we have a bunch of individual fibers here, but we'll just arbitrarily align this one direction, okay? We'll talk about this in just a second. We'll say that E1 is going to look a lot like the Cox model. So VF, modulus of the fiber, one direction. Shear leg parameter A to L, same shear leg parameter as before. But now we have an additional correction factor. It's an alignment factor, eta sub 0. And we're adding to this now. Volume fraction of the matrix, modulus of the matrix. So here's for aligned short fiber composites. Now what is this alignment parameter? Again, ranges from 0 to 1. All right. If it is 1, then this is just the Cox model. Okay. That would make that fully aligned. And if 0, no alignment. Right? So if we're fully aligned, this is just the Cox model. Obviously, frankly.
Quick question.
Question, go.
So, if the alignment parameter is 0, is there a difference between that and random?
Yes, there's a difference. Let me be more clear. The alignment parameter can never be 0, so that will kind of clear things up. Let's be more clear about this. Let's not write. Yeah, okay, we can keep it. I'll say that this is impossible. And I will explain why in just a moment.
All right, sounds good. Thanks.
I mean, having 0 would be the same as just not having a reinforcement at all, right?
By our model, yes. Okay, so let's explain how to calculate this alignment parameter. I'll say typically alignment parameter is obtained from an image of the composite. Okay, and so one example of this might look like this. So I'll bring in the picture here from the notes because my sketching ability is not so good. So I want to know, what is my modulus along the loading direction? So what is alignment parameter in load direction? Okay, that's maybe what you want to know. Well, you could think of an alignment of each individual fiber by defining the angle that that fiber makes with the load direction. So you sort of see this here with this particular fiber. Let's look at this one particular fiber here. You see generally the load is kind of like in this direction. We might assume this to be the one direction. We could, you know, we arbitrarily sort of picked the one direction, right? This just happens to be the load direction that we're after. So let's say that we're going to assign this as the one direction. So this is the one direction. And we're interested in what is the alignment parameter in that particular direction. Well, we can look at a number of individual fibers and check the angle of each fiber with respect to that load direction. Let's call that angle theta I. That is the angle of the ith fiber in this cross-section that fiber makes with the one direction. Okay. What we want to do then is we want to basically count how many of those individual fibers are closely aligned with the one direction, and the more are aligned with that one direction, the closer our alignment parameter should be to 0 or to 1. So the tighter and tighter this angle is towards the one direction, the closer and closer we want this alignment parameter to be equal to 1. So as this angle approaches 0, we want our alignment parameter to be 1. So what trigonometric function approaches 1 as our angle theta approaches 0? Cosine, right? So we would like to see an alignment parameter that somehow uses the cosine of this particular angle to sort of calculate how well aligned this particular fiber is with that loading direction, right? And there are a few models that do this, but the one that is most commonly accepted is this alignment parameter. That a to 0 is the summation from I equals 1 to n. So we're going to count n individual fibers of the number of fibers that happen to be at the angle theta I times the cosine to the 4th power of that particular angle divided by the total number of fibers that you have. So let's make this clear with some writing. Okay. So here, this is the number of fibers with an angle of I. Okay. This is total number of fibers. And this is cosine of the angle associated with the ith fiber, cosine to the 4th. All right, so how might this work? Well, if you have a bunch of fibers at 0-degree orientation, you would have an n for the 0-degree orientation of whatever number that is. If they're all aligned, let's say we count 100 fibers. 100 of them have the orientation of 0 degrees. So 100 multiplied by cosine to the 4th of 0 is 100, divided by the total number of fibers, 100. You would get an alignment parameter of 1. Right? Now, this is never going to be 0 because there will always be some number of fibers that you're going to count. Okay? And the only way it could really be 0 is if they're all at a 90-degree orientation with your alignment. Say if you're loading and you're completely aligned at 90 degrees with the load direction, okay, that's the only situation where it's going to be 0, and that's pretty much impossible. And in that situation, you probably just want to use an aligned short fiber composite for E2, let's say. Okay, so this is generally the alignment parameter and how it's calculated. Basically, I have to count manually. It's annoying, but it is what it is. So the closer this is to 1, the more highly aligned they are, and the better that this is generally going to be, right? Or the more highly aligned that you will see this. All right. So that's your aligned short fiber model. And that's for calculating the modulus in the arbitrary one direction for your composite. Notice here that because we have like this partial alignment, it's sort of up to us to dictate what we call the one direction. And the alignment parameter is going to change as we change what we arbitrarily assign as the one direction, right? So if we happen to pick a loading direction or a one direction that is very highly aligned with the fibers, we're going to get a larger value for E1. If we happen to pick a loading direction that is highly unaligned with the fibers, then we're going to have a very low value, kind of approaching that of the matrix because there's no fibers in that general direction. Yes, sir. Right. So the question is what happens if you have fibers with multiple angles? Well, let's look at an example, and that's where the kind of the summation comes in. All right. So if you have something that looks like this, I've got 3 this way, I've got 3 this way, and I've got 3 this way. Let's say. Okay, so let's say it's a 0, 45, 90. Okay? So your general equation for the alignment parameter would be something like the summation from 1 to n of number of fibers with an orientation of theta I multiplied by cosine 4 theta I all on n. So you'd have 3 components of the summation here. Number with an orientation of 0 is 3 times cosine 4, 0. With me? Plus, I have 3 that are cosine 4, 45. Right? Plus 3 that are cosine 4, 90. With me? All of this gets divided by the total number that you have, which is 9. So the summation allows you to have fibers at multiple different orientations. You just have to count the number that happen to be in that orientation, multiply them by their appropriate cosine 4 of the angle that they have. Is that clear? That's how this is kind of like utilized. So in this situation, I guess you could do the math, but it'd be like, I don't know, 1 plus, I think this will probably be like, sorry, this will be 3. This will be like 3 plus approximately 1.5, I think, plus 0. So this should be about 4.5 over 9. I think this should probably be about 0.5, which is probably a good guess for this composite, if I had to guess. Okay, so that's how you sort of use that alignment parameter. All right, continuing. So that was aligned. Now let's look at random. Yeah, I would say if you got a cross section, you probably want to try to count as many as you can. If you want a representative number, 100 is good. I would write a computer program if I had to do this. Yeah, like some vision software. MATLAB has good vision software tools if you need to do this in actuality. Especially if you have good contrast between your fiber and your matrix. Like carbon fiber and let's say high density polyethylene would be pretty easy to identify. All right, so let's talk about random short fiber composites. Picture you should have in your head for random is how we would say random. Okay. Now, what's unique about composites with sort of this random fiber orientation is you sort of lose the directionality associated. Okay. So actually random short fiber and random particulate composites actually behave like isotropic materials. And that's because they don't really have any associated directionality anymore. So continuous fiber composites that have huge fibers running in one particular direction, yeah, okay, there's obvious directionality to that. But some composite that's made of like a bunch of chopped short fibers that are randomly oriented, on the macro scale, it looks a lot like an isotropic material. Okay, so at macro scale, random short fiber composites behave like isotropic materials. Okay, so whether I load this guy this way, or into and out of the page, or this way, or whatever. I mean, be the genie in Aladdin on the carpet. Here, anywhere. It's going to behave the same in all directions, right? So because of that, the models should reflect that. So calculations for moduli in Poisson's ratio reflect this. And usually when they're labeled, they're given something like E sub random, or G sub random, or new sub random. So what I mean by that, that you should see following models. And they're here more or less calculated over many experiments. So I'll say that these are empirical. Mean they're gotten from experiment. It's kind of what empirical means. So the modulus of a random short fiber composite gets about 3/8 of its contribution from the modulus in the one direction, and 5/8 of the modulus in a two direction of a composite that would be made with aligned short fibers. Okay. So calculate what E1 would be for an aligned short fiber composite. That's help and psi with xi is 2L on D. Calculate what E2 would be for an aligned short fiber composite. That's help and psi with xi is 2. Plug those both into here, and this gives you the modulus of your randomly aligned short fiber composite. Continuing. Looks like maybe I have a question. Recording? Yes, I'm recording. Thank you for that. Making sure I'm recording, that's nice. All right. The shear modulus. Also more or less gotten from experiment. Is 1/8 the modulus of an aligned short fiber composite plus 1/4 the modulus in the two direction of aligned short fiber composite. Again, E1 and E2 from simplified aligned short fiber model. Finally, Poisson's ratio. This is obtained from isotropic material relationships. You may have seen this in 2004 or 3005. Poisson's ratio is a combination of the elastic and the shear modulus. E random over 2G random. All minus 1. This is purely an isotropic relationship. So this holds for all isotropic materials. But here we're assuming, this random composite is behaving like an isotropic material. Okay. very important that you realize here that E1 and E2 in these equations are not for, let's say, the modulus of the fiber in the 1 and the 2 directions. This is the modulus of elasticity in the 1 direction and the 2 direction using the simplified model that we talked about previous lectured, and I kind of draw way back up here. Here's your simplified model with E1 and E2, right? That's for an aligned short fiber composite, way back at the beginning of this lecture. For E1, use xi with the aspect ratio. Right? For E2, use xi equal to 2. Those two calculations feed into the calculations of randomly aligned short fiber composites that you see here. I've seen that mistake many times. All right. So that's going to be the final little bit of information that we sort of talk about for short fiber composites. We'll kind of conclude that. Final comments on short fiber composites? Things that you kind of have to keep in mind for more like practical reasons. All right. Though we didn't really see this in the simplified model, we saw this in the Cox model, that a short fiber is not completely loaded. All right. The ends of the fiber is not loaded. Okay. The ends of fiber don't carry normal stress. Right. We sort of saw that with our little model. The end of the fiber, that's a free surface. Think of like plane stress conditions on the top. If you have plane stress conditions, you don't have any stress in that third direction, which is with like the end of the fiber here. Right? So short fiber, not fully loaded. Also, as your fiber length, average fiber length, gets sort of shorter and shorter and shorter, your reinforcing efficiency is decreasing. And that's because the shorter and shorter the fiber is, the less and less that fiber is capable of fully demonstrating its load carrying capability. Okay? So, shorter fibers have less load carrying capability and lower reinforcing efficiency. In the Cox model, this is expressed in the shear leg term eta L. With that hyperbolic tangent function. Right. Another question? No. Okay. Last thing I want to talk about is particulate composites, and that'll be it for today. The picture you should kind of have in your mind here is kind of like a cube of material with a bunch of dots in it. No other real way to explain it. You got this like cubic epoxy material, and then it's got a bunch of, like, I don't know, spheres in it. It's a cheetah. All right, so these are particulates. All right. Someone make a general comment about how they think this material will behave. Who said that? You win. You win the thumbs up award today. All right. So obviously, because you have these zero-dimensional particulates, I'm calling them zero-dimensional because their aspect ratio is more or less 1. You still retain that isotropic behavior on sort of the macro scale. All right. So here, if we assume an aspect ratio of 1. So more or less spherical inclusions. All right. With spherical inclusions, we'll see that we're going to approach isotropic behavior. So this leads to isotropic behavior. Then the question is, how do we calculate that isotropic behavior given the materials involved? Okay. So we know that generally our properties are governed by, the bounds of what we might expect for our properties are governed by rule of mixtures and inverse rule of mixtures, right? We sort of saw that with continuous fiber composites. So here we know our properties of composite bound by rule of mixtures on high end and inverse rule of mixtures on low end. So we would expect that the property of the composite should fall somewhere in between, like the property given by the series model and the property given by the parallel model, right? So let's say we have some property of interest that we care about. The prediction that we might get from the series model is going to be on the low end. And the property that we might get for the parallel model is going to be on the high end. Right. It's interesting here, like particulate composites are like it's like a whole, they're their own entities. They're their own beasts, okay? And that's because sometimes particulates are softer than the matrix phase to help increase the toughness overall of the material. Sometimes you have a soft matrix phase and you incorporate hard particles to give it stiffness. So you really see particulate composites, with low stiffness inclusions that might be used for toughness, or high stiffness inclusions that might be used for strength. So the benefits that you get from including particles can really go both ways. All right. I'll make a note of that here. Let me see. High stiffness inclusions. Generally low stiffness matrix. This would be like what we've been talking about all along. We have high stiffness glass fibers and low stiffness epoxy matrix. It's sort of like what we've assumed this whole class so far. Okay, sure. in this case, it's closer to series model. You may also see low stiffness inclusions in a generally high stiffness matrix. That might be like including rubber particles in an epoxy, right? So rubber generally has a lower modulus than epoxy. You know, most rubber's on the order of, I don't know, 5 to 50 MPa is, you know, maybe appropriate for its stiffness, whereas epoxy is on the order of 2 GPa, all right? So low stiffness inclusion might be included to help you with toughness of your matrix, all right, to stop crack propagation. It's a lot easier to rip open just pure epoxy than it is to rip open rubber toughened epoxy, okay? So ergo, rubber and epoxy. So in this case, approach property is governed by parallel models. The point is we need like flexible descriptions, okay? And the most flexible and most commonly accepted sort of model that we have is called the Lewis-Nielsen modification. And it basically uses an adapted form of Halpern-Tsai equation. Lewis-Nielsen. I before E, except after Lewis, N. Just kidding. This is specifically for particulate composites. And this is a modified Halpern-Tsai equation. Here's the form. The property of your particulate composite is the property of the matrix multiplied by 1 plus xi, eta, and let's be specific here. Let's make some subscripts. Xi, what they say, PL is usually the subscript. Eta, P, volume fraction particles, over 1 minus another parameter. This is psi, S-A-I, as opposed to xi. Don't get confused. Eta, VP. Here's your general Lewis-Nielsen approximation. So let's define these things. Xi PL is 2 times 1 minus Poisson's ratio of the matrix divided by 1 plus Poisson's ratio of the matrix. This helps you sort of describe the relative, like, how do I want to say this? Absorption ability of the particulates to absorb energy. That's why it's sort of using the Poisson's ratio here. We have this eta P, which will look familiar. property of the particulates divided by property of the matrix minus 1 over property of the particulates divided by property of the matrix plus xi PL. And finally, the psi term, 1 plus 1/2, 1 minus volume of particulates squared. All right, complicated. Sir. Yep, thank you. Yep, thanks. Okay. So generally this model good for modulus E and G, but not for Poisson's ratio. It's not the best for Poisson's ratio. And again, I'm not specifying a direction here because it's an isotropic material, we're assuming. Also, only good for particles on size order of let's say 1 micrometer to 1 millimeter. Breaks down with nanoparticles. No nanoparticles. No, no, no. They put the no in nanoparticles. Okay, that'll be it for today. I'll leave this here and say shalom and have a good day.
Dr. Hart, can you scroll up for the eta equation real quick, please?
I can. This one?
Up a little more.
Sorry, guys.
Yes, thank you.
Austin. Someone in the chat is still. Just give me 30 seconds here.
I'm good, thank you.
Okay, we got it. Size on order of 1 micrometer to 1 millimeter. This is micrometer.